So let's take a look at some applications of Gauss's law. We derived this carefully last time. Before that, though, I'd like to just say a few words. And you remember we derived first the differential form of Gauss's law, which is basically the divergence of E is equal to this argument of the volume integral. By integrating both sides, we were able to use the divergence theorem to prove the integral form of Gauss's law. Now, one thing that you have to realize is what this surface can be. Finite region, there's some charge there. It might be point charges, line charges, surface charges, volume charges, all with appropriate values and densities. So for the various distributions, you'd have lambda, sigma, or rho. Gauss's law holds for any closed surface. So in other words, the collection of charges, so all different kinds. So the yellow might be a volume, these two may be surface, and then you have some line charges and then point charges. We can have the surface that we use for this side of the Gauss's law be outside, so you have totally outside all the charge. You can be totally inside, and that's also legal. If you realize what this means is that all this charge outside has no impact on Gauss's law. So if you integrate that E field over that surface, you will get the Q enclosed over epsilon naught. But you say, wait a minute, if I have charge out here, that's going to create flux lines that pass through this surface. That's very true. But if, for example, this point charge has a flux line like this, it both enters and leaves this surface, so it contributes nothing to the total flux evaluated on that surface. That's why we can talk about Q inside being equal to the total flux passing through the surface S. Well, likewise, you can have both inside outside. So the surface that I show here has regions that are inside and has regions outside. All three of these are true. Does that mean you can use them to get the E field? Well, the way I've drawn them, not very likely, at least just by doing integration, because you can't do the integral. Here's one we can do. This is the infinite sheet of charge. We're talking about, say, something like this, where in reality these extend to infinity in these directions like this. What we want to find is the E field due to this surface charge density. It's uniform and makes things a lot easier. So let's take the z-axis normal to that surface. So what we do is we apply the idea of a surface for Gauss's law that consists of what we call a pillbox. And the pillbox has these ends with area A, and we call this one S1. And here's another one with the same area A, and we call that S2. And so if we first define the vectors that represent those surface elements, vector S1 and S2, and notice that they are in opposite directions because the vector that you use for the integral for Gauss's law is always coming out of this closed surface. Just remember that on the sides you have ds vectors that point in this direction, normal to that surface. Okay, so A is the area of these end pieces. So by symmetry, this infinite sheet will generate a E field that is normal to this surface. So that shows you that you have E in the z direction, either plus or minus, depending on what side you're on. So for sigma greater than 0, this is outward from the surface on both sides of the surface, and I've drawn these on two sides. What I just told you can be determined by considering just a ring of charge. There we showed that it gave us E perpendicular to the ring for a point on the axis. And so if you take the argument and say that the entire infinite plane E could be made a superposition of rings, therefore the E field of the plane is normal to the plane. And so you have EZ only. We could have used a disk, by the way, because we know how to find the E field of a disk. You get come to the same conclusion. The other thing that will help us is that the E infinite plane is constant in magnitude, so it's independent of Z. To see this, we use the fact this is normal to the plane, which we just talked about, so it's EZ only. We take this pillbox and we just let H change. So you can have it very small and you can have it very large. But because E is perpendicular to the plane, it's also perpendicular to these surfaces. So what that means is that the total flux through the ends here, this end and this end, remains the same no matter what H is. If that's the case, then the E field does not depend on H, and so we would say then that we get an E field that is independent of Z, and that's true on both sides of the charge sheet. Well, these two consequences really help us in determining the E field. So here's our picture again. We first conclude that E dot ds along the sides of the cylinder or the pillbox is 0 because there E, which is normal to the plane, is perpendicular to ds, where ds is parallel to the plane. Consequently, we don't have to worry at all about the flux going through the sides of this pillbox because there isn't any. For both the top and the bottom, we can get the flux through each surface. It's going to be the absolute value of E times A because this is parallel to A and it's constant over that surface, and so therefore it just equals the magnitude of E times A. For the whole surface, the total flux will just be 2 times that, and the reason is because the flux is a scalar, and so we determine the flux through the top and then through the bottom. They're identical, we add them together, and so we get that factor of 2. And all of this results because E is parallel to ds and is a constant over the whole surface S. The total flux is equal to this. That's the left-hand side of Gauss's law. So we have the left-hand side, so that's this side over here. So now we're going to attack the right-hand side. Well, that's pretty easy because the Q enclosed is just equal to the area of this intersection of the pillbox with the charge sheet times the sigma. Sigma, remember, is a constant. It's the same value over the entire surface. So we have the right-hand side then is the Q enclosed divided by epsilon naught. We've already got the left-hand side. So we can set those two equal to each other, which I've done here, solve for the magnitude of E, and that's simply sigma over 2 epsilon naught. We know that E is going to be in a normal direction, so we can write it like this. Now remember, the normal direction switches direction from this side of the plane to this side of the plane. So in terms of the field lines, you'll have a bunch of parallel field lines on this side going up and on this side going down, and the magnitude will just depend on the density of charge on that surface. Let's consider a variation on this where we have 2 charge planes. And so I've shown them here as a plane of plus and a plane of minus, and these are drawn finite, but they're supposed to be big enough that we can consider them to be infinite. They're separated by a distance d, and they have uniform sigma, plus and minus, on those 2 plates. So the problem is to find E everywhere in this space. We're including between the 2 plates, and then on the outside up here, and the outside down here. So we've got 3 regions that we have to worry about. To attack this, consider the problem that we just looked at, and that was the field due to a single charge sheet. And so you'll notice that the field lines look like what we drew before. They're going away from the positive charge, like this. And so the magnitude of this field up here would just be related to the sigma on that plate. And then over here we have a minus charge sheet. So all the field lines go into that charge. And so below they come this way, and up here they come up here. So that's what the field looks like alone. But we're going to put those 2 together in this geometry here. So if we look at the fields from these 2 charge sheets and put them in this orientation, what's important to realize is that the fields from each of these charge sheets extends to plus or minus infinity in the z direction. Okay, so think about this. This field here, which is pointing down, passes right through the charge and continues to minus infinity. This charge here terminates on this charge here, but comes from minus infinity. This charge here starts with the charge sheet and goes all the way down this one goes negative all the way up. So when you think about it, you have up here, before we superimpose these, you have this magnitude here for the field. Here we have minus this quantity, minus this quantity, where the sign simply just reminds us which direction these fields point. So if it's plus, it goes up. If it's minus, it goes down. So just consider the region between these two charge sheets. What we're doing is adding these two fields. So in other words, this plus this will give us the total in this region. Down here we have this field superimposed with this field. This field here will cross over into this region here. So we're going to end up adding this to this, and of course we're going to get 0. So let's take another look at these in terms of adding all these things. Now this is a little complicated. First we'll go inside. So inside we have this field here coming from this positive charge here. We have this field here coming from the negative charge. So that it's coming between here and here. Because this is the negative charge here, that field will extend all the way to plus infinity. And so it will be up here, it will be here and here. Likewise, over here, we're adding this plus this out here. So we're adding this here, that's going up. So that's this one right here. This is the contribution from this field here terminating on the minus charge. This component here is coming from this part here. This extends from here to minus infinity. If we go up here, this contribution here is coming from here, and this one here is coming from here. So you add those two together, and you'll have one going up, one going down to the same magnitude. You get 0. Inside, we've already shown that if we take those two fields, namely this one and this one, we'll end up with minus sigma over epsilon naught z. The 2 disappears because we're adding this one and this one. They're both in the negative direction, so we get a minus sign, and of course the z hat. Finally, we see that we have these two adding together, canceling, and so we have 0 field there. So the net result then is putting these together. If we look over here, we have a field in the center. We have 0 field out here and 0 field out here. The idea that we're terminating the flux, so we're starting at plus charges and terminating on the minus charge, is certainly valid, and because they're equal, you would expect then that the flux lines starting here would end here. But I think that this is a more universal way of looking at it, so where you're adding the fields that are allowed to penetrate these charge sheets and show up in places where you would expect them to, namely this one will go to plus and minus infinity, this one will go to plus and minus infinity. This summarizes then the two fields up here add to 0, two fields here add to 2 times the field from one of the sheets. It's in the minus z direction simply because it's plus here and minus here. And then finally down here the two fields add to 0. That's the way to look at these charge sheets that have opposite signs. Let's look at another problem, and that is an infinite slab of uniform charge density. I show you here this slab where you have a material with a constant rho. The width is 2d here, and it extends in both the z direction and the x direction to plus minus infinity. The y direction has the finite width of this slab, and so that goes from minus d to d. What we're interested in then is finding the E field for the regions where we're outside, so that's this one, and then inside, which is this interval here. We're going to use Gauss's law to solve this problem, and so first we want to find the E field outside. So to do that, we put in a pillbox, and in this case we put both ends of the pillbox outside of the charge. The surface S is the total surface enclosing this volume here. Well, we know that the surface elements on the outside of the pillbox that are oriented here will have vectors ds pointing in this direction, and here ds in this direction, because they have to point outside of the volume. the area of each side or each end is A. We can think of this sheet as we did before as a charge sheet, except let's say you have a bunch of them in parallel like this. Now the only reason I introduced that is we want to use the same symmetry arguments that we did before. So if we're adding up parallel charge sheets, the E field should have the properties of a single charge sheet, and that is the fact that E is normal to each sheet, E equals EY only, outside the slab so that we don't have any change in the amount of charge, say within a pillbox that contains the charge. We have the outside the slab, E is independent of Y. So it looks like one charge sheet with a surface charge density that we'll calculate. So we expect inside that E will depend on Y because it will depend on where you put the Y value to determine the field. By superposition, E both inside and out is parallel to the Y-axis. In the case where we have a constant positive row, then ds and E are both parallel and in the same direction on each side. So that's what I show here. E will be parallel and in the same direction over here if this is plus. E will be parallel and in the same direction over here if this is plus. For the same reasons that we've talked about before, there's no contribution to the flux on the sides because the ds vectors are normal to the direction of the E field. We can ignore the entire sides of the pillbox in terms of the flux. We only have to do with the ends. So let's apply Gauss's law for this surface S. And first let's look at the left-hand side, and because we have E constant over that disk here, it's a constant value over these two sides, we can write this as 2E outside times A. And the 2 comes from the fact that we get equal contributions from this disk here and this disk here. Remember that E is in this direction over here, E is in this direction over here, so they're both parallel, and you'll get a plus value here and a plus value here. The right hand side has to do with the Q enclosed divided by epsilon 0. So what is Q enclosed? Well, it's the density. By the way, I put zeros on here just to remind us that that's a constant. So rho 0. If we look at this, this will be 2D times A. Well, 2D is the length of the region where there's charge, and A is the area. So the volume of this region right here, that volume is 2dA. So you multiply by rho 0 times the volume, and that gives you the charge enclosed. And of course we divide by epsilon 0 to get the equality. Well, it's a simple step to get the E outside, and so it will have this expression here. Okay, so now we'll change to vectors and realize over here it's heading in the minus y direction, over here in the plus y direction, and so we have this minus sign here and plus sign here for the left side and for the right side. So those are the fields outside, and you can see that they're constant. They do not depend on the y value. Now we'll go inside. And so what we're going to do is move the pillbox so one of the surfaces is outside, we'll call it S1, and one is inside, S2. We'll put it in this position, but realize that could have put it anywhere. And we're going to have the end of the, let me just draw it, we're going to put this end here at Y. Realize it could be over here, and the only difference will be Y will change sign because here's the origin right here. We already know what E outside is on the left. We're going to just call E inside E inside. We apply Gauss's law for this particular surface, and so we'll have to evaluate this, and then we'll evaluate this again. Here's the right-hand side. The right-hand side consists of the E field on the first surface plus the E field on the second surface integrated over the surface. So what we're talking about is E1 here, which we'll draw like this, and E2 here, which it depends on where you are, where Y is, but right now let's just say in this direction. It's certainly going to be parallel to the E1. So if you look at the integral then, E1's constant, its magnitude will be E1 times A, and realize the reason we get plus is because the area element is in the same directions, and likewise over here the area element is in the same direction as E. Total flux will be this plus this. So here we go. We have E1 times A and then E inside times A. The right hand side again is equal to Q inside over epsilon naught. Q inside is going to be the density times the volume where there is charge inside the pillbox. Well, it's going to go from Y to minus D, so the length of this part of the cylinder is D plus Y. So that's right here, D plus Y, and then of course times the area. So this is the volume of charge that's inside that pillbox. So we multiply the volume by rho 0, we get the Q inside divided by epsilon 0, and so we can put it all together. Here's the left hand side and here's the right hand side. We can divide by A. Then we have one more thing to do, and that is we identify this as a E field outside of the charge distribution. And that's what we solved in the step before, and that was equal to this quantity here. We can solve for E inside by substituting that in, and so here it is at this value here minus rho 0d over epsilon naught. The minus sign is because it's in the opposite direction to this value here. Solve for E inside and we get this quantity here, which does depend on Y. The other thing to realize is that Y switches sign when you go from one side of the origin to the other, and so that's going to be useful. If you plot it, it looks like this. The magnitude and direction of E outside is shown here, and I plotted this so that this is minus and this is plus, just so we're plotting this quantity here, the magnitude with the right sign. Inside you have this expression here. You'll notice that when Y goes from one side to the other, we get opposite signs. So the switch in the sign of Y takes care of both sides of the origin. So in other words, the change in the direction of the vector is taken into account by the sign of the Y. So this is correct, and over here it's plus, over here it's minus. It's heading in this direction, over here it's heading in this direction. That goes up, 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 up until you hit the edge of the slab, and then you have a constant E field. There's no discontinuity here. There's no discontinuity here. So this is the general solution then of this particular problem. So next time I'll give a few more examples using Gauss's law, where we'll introduce some other geometries other than these planar geometries.